Okay, last call. Get your vote in. Okay, good. A lot of us got that right. So what we're comparing here is the tension force by the cord on the ankle to the tension force by the ankle on the cord. Do you hear the sing song? Do you hear the indices get up and switch places there? Those are equal and opposite by Newton's third law, by Newton's third law. Okay, and that's what we talked about last Thursday. So here's another question, a different question. As the bungee cord slows you down, the force of the cord on your ankles is greater than, equal to, or less than your weight. It's a different force than we were comparing before. So you can click now. Okay, that's about all of us. Last call. Good. 87% of us got that right. Here we're talking about two forces that are on the same free body diagram. And remember, we always have two vectors that represent the motion of the individual or the object. We have the velocity vector, which is down because you're still moving down, and the acceleration vector that's up because you're slowing down. Well, one of those we have to ignore, okay? We have to ignore the one that's very, very obvious. I mean, that's the one we can almost see with our eye, but that's the one that we don't care about. We have to worry about this acceleration vector. And that means that our free body diagram has to scream that acceleration or up. And that means the force by the cord on Greg's ankle has to be bigger than Greg's weight. The diagram has to scream up. I have to have more force up than down. And that's by Newton's second law. And whenever you invoke the second law, you have to finish your sentence with acceleration up. You have to qualify it. Check that your neighbor's on the bus with those two problems, because that incorporates all of the second law and the third law, which is all of mechanics. Okay, let's have a pop quiz. Again with your clicker. Newton's third law does not apply if a system is accelerating. True or false? You can click. Okay, last call. Oh, I'm sorry, that's not the answer. Oh, the answer is way false, completely false, totally false. Newton's third law always applies. It applies in every situation, Tuesdays, Thursdays, Sundays, every way, which way, okay? So, second question, Newton's third law companion forces never act on the same object, true or false? You can start clicking now. Okay, I think that's all of us. Good. True is the correct answer there. Okay, true. One of those, remember, one of those forces was hurting John's jaw, and one of those forces was breaking my fist. They always act on different objects. Let's try this one. Contact forces have third law companions, but gravitational forces do not. True or false? Who are my helpers over here? Who's willing to help? Thank you. Any more helpers over here? Thank you very much. On this side? Yeah. Okay. Got helpers. Okay. Oh, whoa, we got some extra people in the class. Okay, that is again wave fault. Every force in the universe comes as a match set. They're all married. They all come with an equal and opposite companion force. What I'm handing out is a pretest on one side and an old exam question on the other. We'll work on the old exam question at the end of class today. But for now, just look at that pretest. You are pushing this crate across a rough floor. The crate has lots of nooks and crannies. It's rough. And the rock has lots of nooks and crannies. It's rough. And you're pushing that crate across the floor at a constant velocity. A constant velocity. And so you're asked to draw free body diagrams for the crate and the rock. Now remember, I asked you to put something in your toolbox. And that was when things are touching, you always draw the free body diagram of the simplest object first. The thing that's touching the fewest other things. So which free body diagram you want to start with? The rock. Yeah, the rock. Okay. So go ahead and fill out that pretest. You won't turn it in, of course. Raise your hand if you don't have a pretest right now. Looks like we're good. Thank you. Did you get one? Okay. Thank you. Appreciate it. Thank you. No, buy on. Buy on. I know that many of you are not finished with that yet, and that's okay. You've all had a chance to think about it, and that's what we need today. If you could finish that before coming to class on Thursday, we'll talk about the answers to that on Thursday. But today we're going to use your free body diagrams to help introduce this idea of friction. What we know about friction already is that it's always parallel to the surface between the pusher and the pushee, okay? It's always 90 degrees to that normal force because the normal force is always perpendicular to that surface. What I mentioned, but we didn't go into, is that it comes in two flavors, static and kinetic, or as I like to call them, hard and easy. The static friction is one of the more complicated forces. We're going to talk about that at the end of lecture today. But the kinetic friction is just brutally simple. Static is when I'm pushing on something and it just doesn't go anywhere, where there's no relative motion between the surfaces. They're stuck together, okay? Whereas kinetic friction is easy to recognize if you still have your hearing. I don't, but you do. You can hear it. You heard the scraping going on, and that's the kinetic friction, where the nooks and crannies of the bottom of that bucket are scraping against the nooks and crannies of the tabletop. You can hear it going on. So let's talk about the easy kind first. Start with that. As I slide this across, what things should that force depend on? What attributes of this bucket or this table should that depend on? And I'll give you a clue. It's not the color of the bucket, okay? So talk to your neighbor. What sort of things should matter when I'm calculating that kinetic friction? What should matter?
I don't your friction. I know that there is like a.
Okay, brave soul, raise your hand and share. What's going to matter? Where are you, brave soul? There's a brave soul. What matters?
Types of surfaces.
What kind of surfaces they, whether they're rough, whether it's hockey puck on ice or sandpaper on wood.
To just what the normal force is.
What the normal force is, okay? What else?
Say the weight or mass.
The weight or mass, okay. What else?
Surface area.
The surface area, what else? Anything else? The coefficient of friction, okay, we're going to introduce that concept in just a moment here. So all of these things seem reasonable to me. In my mind, the friction force should depend on all of these things. And yet we've been given a tender mercy. We have been given such a blessing in that it turns out that this friction force only depends on the types of surfaces that are in contact, how rough they are, which we're going to find out gets folded into this coefficient of kinetic friction, and the push between the surfaces, the normal force that is exerted by one surface on the other surface. And that's it. And that's it. Now, I think the surface area should matter. I mean, after all, we're talking about nooks and crannies that are scraping against other nooks and crannies. And if I'm sliding this object this way, I've got a big surface area with lots of nooks and crannies. Whereas if I slide it this way, I've got a few nooks and crannies that are interacting. I think that should matter. Now, sir, what's your name? Willem, can I push on your hand with about 2 pounds of force?
Yeah.
With on your arm rather, the arm. Now, what if instead of pushing with my hand, I had come towards Willem with a great big long needle? What would you say then? Probably no, yeah, probably not, yeah. And that's the difference between force and pressure, okay? In both cases, it would be a push of 2 pounds, but in one case, the 2 pounds is spread over the surface area of my hand, whereas in the other case, it's all concentrated on the head of that needle, okay? And that's what's going on here. When I slide this way, I've got lots of nooks and crannies, but the pressure is not that great. Those nooks and crannies aren't being pushed into each other as much as if I slide it this way. I've got fewer nooks and crannies, but now the pressure is great. It just so happens, who saw it coming? That cancels out. That cancels out. You had your hand up?
Why wouldn't weight matter? Because if you're like pushing on those crannies more, like the downward force.
Well, you remember that when this is sitting here, the weight down and the normal force up are equal and opposite to each other by what law? Second law with zero acceleration. So indirectly, the weight is going to be important. But we'll find out that in some other cases, like when you're on a hill, the weight and the normal force are different from each other. And it's the actual physical push between them, the normal force, that is what matters. Now, many years ago, my dear wife decided that she was going to sit in on my class and learn physics. She just thought that would be fun. And we decided not to tell the students in the class, and she went to tutorial. She interacted with all the young students and everything. And we almost got away with it. But then there was a big fancy ballroom dance at one of the big hotels. And my wife and I just loved dancing. And we went and we were just twirling away, having a great time. And every time we twirled around, there was a student from the class, and there was a student from the class. And I thought, oh, this is awkward. And the next day in class, we were talking about friction. And we were talking about how simple it was and how it didn't depend on surface area. And my wife's hand went up. And I thought, oh, this is bad. She asked hard questions. And she said, Professor, if what you say is true, why is it that when we file down the wheels on my son's Pinewood Derby car to a point, he wins? Now, I know the answer. The answer has to do with rotational inertia. We're not going to cover that until the end of the semester, and I don't want to go there. So I figure it's time to come clean. I said, well, that would be my son's Pinewood Derby car too. Class, I have a confession to make. I'm sleeping with one of the students in the class. She also happens to be my wife of 20 years and the mother of my 4 children. Now it's 48 years, but anyway, what they were interested in was that she wasn't taking the class for a grade. But it's true. It turns out that it just doesn't matter. The surface area doesn't matter. It's a gift. Now, how do I measure kinetic friction? If it's all of these nooks and crannies interacting and they're interacting by a different amount, how do I figure out how big that force is? Well, we can do it through this pretest, okay? If we use the fact that it's moving at constant velocity and we just ignore the vertical forces, they're simple. Let's just look at the horizontal forces on the crate. And I'm going to get rid of that rock for now. We'll bring it back. We'll bring it back when we talk more about this pretest. But if I just look at the crate, I have the push by the person to the right and the friction force to the left, and I made that smaller because it's moving to the right. I'll wait. Is that wrong or sick and wrong?
Thinking wrong.
Sick and wrong. If I'm moving at constant velocity, that's zero acceleration. This diagram has to scream balance. That friction force is just as big as the push by the person. And that's the key, because I can measure the push by the person very, very easy. I just put a bathroom scale between his hands and the crate. And whatever the reading is on that bathroom scale, that's the force that he's pushing with. And indirectly, by Newton's second law with zero acceleration, that's also the friction force, okay? Now, we're gonna do a simple experiment. We're going to take a block and pull it across the floor, and we're gonna change the normal force between the floor and the block. But we're gonna move it with zero acceleration, constant velocity. Now, instead of a block, I'm gonna use this sled. And I'm going to need these three people to come up and help with this. Okay. Thank you. What's your name? Corinne? Tori. Well, I wasn't even close. Okay. If you could stand on the sled, and gentlemen, your names are Evan and Ben. Evan and Ben are going to hold your hands and make sure that you don't fall down on Sue the University. Okay. Now, what I'm going to do is I'm going to pull her at constant velocity, and we're going to look and see what force is required to keep her going at constant velocity. Now, I don't want you to look at this while she's speeding up, just while it's a constant velocity. So everyone close your eyes, except for you three. You keep your eyes open, okay? Keep her alive. Okay, everyone close your eyes, and I'll get Tori started here. Okay, open your eyes. Okay, so that was about 100 pounds, 500 Newtons sounds even more impressive, right? Okay, let's back up. Okay, this time we're going to put Evan on there. Okay, and you two keep him upright. I'm going to need some help. Okay. Yeah, all y'all. Okay. Yeah, you just got to grab onto this and get him going at constant speed. Okay. Okay, now you can open your eyes. Whoa, okay, up at 150 pounds. Okay, let's give them a hand, folks, all of our helpers here. Now, if we plot tension as a function of normal force, what we find is if there's no normal force, there's no tension in the cable. It's just very simple to move. And we find that when we put Tori on there, we don't need much tension. And then as we put more and more normal force on there, we eventually get to Evan over here, and we need a lot of tension, okay? But it turns out to be a linear relationship as long as the two surfaces remain the same, okay? Now, we're plotting tension, but if we are moving at constant velocity, we're also indirectly measuring the friction force. And so what we see is that the friction is proportional to the normal force. That's what the straight line means. And we also find that if I could have gotten Tori going twice as fast, what we would find is that there would be no difference in the friction force. That friction force doesn't depend on how fast the surfaces are sliding relative to each other. Now, folks, that's up to a point. Your gut knows that when you spin those wheels on the drag car and they start smoking, that you're going to change the friction. That's why they do it. They're getting those wheels so hot that they get all rubbery and sticky and everything so that they can really get some traction going. As long as you're going at reasonable speeds with reasonable surfaces, this friction does not depend on speed. That makes sense? Now, since I have a straight line graph, I can represent that as the friction is just equal to the normal force times a constant. And we use this symbol, mu, Greek symbol mu, sub k for kinetic. We're going to find that there's also a mu sub s for static. The friction force is just equal to the normal force times this constant. And let's try to understand what that constant means. Well, if I had put sandpaper on the bottom of this sled and repeated that experiment, which graph would I get with the sandpaper? Would I get this curve here, or would I get that curve there? Which would it be, the upper one or the bottom one? Tell your neighbor real quick. Okay, I hope it's obvious. If that's Tori, if that's the normal weight with Tori on the sled, by putting sandpaper on the bottom of there, we're going to get more friction. So it would be this graph up here. Now you know that that constant is the slope of the line. And so what that means is that this one with the sandpaper has the bigger slope and hence the bigger constant. And that constant then represents the roughness of the surfaces. That mu sub k, we call it the coefficient of kinetic friction, is a measure of how rough those surfaces are. And it's a different number for every two surfaces. Sandpaper on wood, hockey puck on ice, hockey puck on cement, every two surfaces. Now, it turns out that there's no supercomputer in the world, in the universe, that is strong enough, sophisticated enough to calculate one of these coefficients of kinetic friction. There's just too much mess there. And so it has to be measured experimentally. Some poor engineer has to just go ahead and try every two surfaces and find out what the coefficient is. It's the most boring job in the whole world. And the other thing that we know is that it's just a number, just a number. If I go back to that equation, friction is a force. That's in newtons. The normal force is a force. It's in newtons. And that means that this mu sub k is just a pure number with no units whatsoever. It doesn't have any units. It's just a number. And some people mistakenly believe it's a number between 0 and 1. Not true. It's a number that's bigger than 0 and above, but you can make it as big as you want if you use super glue, okay? So it doesn't have to end at 1. It can get big. It can get big. Okay. Questions so far? The good news is it always follows that equation every single time. And that equation will be on the front page of the exam. Okay. Now, I've got this block sitting on a table. Is the weight as a normal force equal to the weight? And I pushed the button too quick, gave away the answer. Yes. Okay. By Newton's second law with zero acceleration. Well, what about now? If I put it on this ramp, this incline, is the normal force equal to the weight now? Yes or no? Yeah, heck no, heck no. Okay, and I can show that with a free body diagram. Okay, the first force I put on any diagram is the weight force, Earth on the block. And then I ask, are there any magnets in this problem? No. So what touches that block? The incline. Does it push or does it pull? Not a string, not a thread, not a chain, not a rope. It pushes. Whenever one thing pushes on another, there will always be a normal force, by which we mean perpendicular to this surface between the pusher and the pushee. Okay, and that means it would have to go in this direction. Whenever one thing pushes on another, there will always be a normal force. There may also be a friction force. If I told you that this block was moving down the incline at constant velocity, would there be a friction force? Yeah, we know that with the dry ice, without friction, it's going to speed up. So there must be a friction force there. Now, folks, you're going to have problems in your homework and on the exam, I promise you, that deal with inclines, hills, ramps, and those are very, very difficult problems requiring you to solve two equations and two unknowns. Messy, messy math. Unless you look at the problem just right. And I'll show you how to look at the problem just right. Okay? You have to tilt your coordinate system to line up with the hill or the ramp or the incline. And if you do that, all of the forces in your diagram are going to line up with either the x axis or the y axis, except for one. But it's always the same one. It's always that weight force every single time. Now, folks, I'm an old man. I've played this game a lot, and I've seen a countless number of ways to break that weight force up into its x part and its y part, its components. But there's only one way that I like to call the correct way. And so I would like you to learn the correct way. What you do, listen up. If you're asleep, wake up now. Look in the direction of the normal force by the hill or the incline and go the other way until you can make a 90-degree turn to get to the end of the weight. If you do it that way, if you break it up that way, you are guaranteed that this angle here, the angle of the hill, will be equal to this angle here between the y component of the weight and the total weight. Every time. That's what you want to do when you've got a problem with a hill or a ramp, to make it simple so that you don't have to do fancy math. Okay? Now, once I have broken that weight force up into its parts, I throw away the original and I use the parts. And if this is coming down the incline at constant velocity, zero acceleration, that means in the y direction, the normal force is just equal to the y component of the weight. The friction force is just equal to the x component of the weight. And that means that the weight force is going to be greater than the normal force. Okay? Now, I hope you can see that as that angle gets bigger and bigger and bigger, this y component is going to get smaller and smaller and smaller. And that means the normal force is going to get smaller and smaller and smaller. Now, the friction depends on the normal force. And that's why in Switzerland, when you get up into the mountains and you look at one of those Swiss chalets, they have a very steep roof. That's because with that steep roof, with that large angle theta, the normal force between the snow and the roof is very small, which means the friction between the snow and the roof is very small, which means very soon the snow is going to slide off of that roof before you get so much snow that it crushes your roof. That's why you want the steep angle on that roof. See if your neighbor is on the bus and wants to go to Switzerland.
Good icon. Yeah, I'm sure it makes sense.
Okay, this is a problem that's very similar to one of your homework problems. You have a 70-kilogram skier coming down a slope and speeding up as she goes. The slope happens to be angled at 37 degrees. Why wouldn't it be? With respect to the horizontal. The coefficient of kinetic friction between the skis and the snow is 0.1, fairly good skis. What is the skier's acceleration? Well, what we know is that her mass is 70 kilograms. The coefficient of kinetic friction is 0.1. We've known since that first tutorial that her acceleration is down the ramp if she's speeding up. We just need to know how big it is, okay? Now, this is just like every other dynamics force problem. The first thing we do is draw a free body diagram. And the first force we put on that diagram is the weight force by the earth on the skier. Then we ask, are there any magnets? No. What touches the skier? The snow. Does it push or does it pull? It pushes. Whenever one thing pushes on another, there will always be a normal force, which is going to be perpendicular to this hill. There may also be a friction force. And by giving that coefficient of kinetic friction, I know there's a friction force. So I put it on the diagram. I know that's the correct free body diagram because I followed the recipe. I know I can trust that recipe. Well, now I need to rotate my coordinates. Oh, I know the weight force is just the mass times 10 on this planet. Well, on that fictional planet, it's 9.8 on our planet, but we're always going to call that 10. So the weight force is going to be 700 newtons, 70 times 10. Now, if I bring down a coordinate system with the x coordinate lined up with the hill, all of my forces are lined up with either the y-axis or the x-axis, except for that weight. So I break up the weight force by looking in the direction of the normal force. I go the other way until I can make a 90-degree turn. There's the 90 degrees right there, and get to the end of the weight. Now, I break that up into its y part and its x part. Which angle is 37 degrees? Well, Greg told you it would be this angle between the y part of the weight and the total weight. But why? Do I just trust Greg? That seems like a foolish thing to do. Okay. Well, let's look at it from the perspective of this board that we drive a spike through and we hang a plumb bob from. Okay. A plumb bob is just a weight on the end of a string that always just points straight down. Now, if I lift up the left end of that board, I bring the board up away from horizontal. But at the same time, I'm bringing the spike away from vertical. And because the spike always has to be perpendicular to the board, whatever angle I bring the board up, I'm going to bring the spike the same angle away from vertical. So these two angles always have to be the same. Does that speak to your soul? Does that make sense? Okay. Now, what does that have to do with our skier? Well, if we think of that spike as the y-axis, then the spike direction is the direction of the y component of the weight. And the plumb bob is in the direction of the total weight. And so that angle is going to be right up here. This is the spike. The red arrow is the spike. And this is the plumb bob right here. That makes sense? Okay. Now, once I have that angle, I can use my trig function. Okay. This side is going to be 700 times the cosine of 37. That turns out to be 560. This one's going to be 700 newtons times the sine of 37. That turns out to be 420. Okay. Now, you can also say that this is a 3, 4, 5 triangle, where this is 3 times 140, this is 4 times 140, this is 5 times 140, whatever. Now, once I have my weight force broken up into components, I throw away the original and I use the components. And whenever I finish a free body diagram, I get to use Newton's second law twice. Once in the y direction, whatever I'm calling the y direction, and once in the x direction, whatever I'm calling the x direction. In the y direction, None of that acceleration is in the y direction. That's why I chose my coordinate system the way I did. And that means I have to have balance in the y direction. I've got one force in the negative y direction that's 560 newtons. My one force in the positive y direction must also be 560 newtons. Fair? That makes sense? That's balance. Now, once I have that normal force, I can find the friction force because I have that simple equation for kinetic friction. I just take this coefficient and I multiply it by this normal, and I get 0.1 times 560 is going to be 56, right? You can do that in your head. You're just taking a tenth of 560, move the decimal place one place, okay? Now I can use Newton's second law in the x direction. I have one force in the positive x direction, 420, so I add it as a positive quantity. I have one force in the negative x direction, 56, so I add it as a negative value. I'm adding vectors. And that has to equal the mass times the acceleration, and that gives me an acceleration of 5.2 meters per second every second. And my friends, my young friends, that is the goal of skiing. Trust me as a parent. The goal of skiing is to keep your acceleration smaller than 9.8, okay? Smaller than 9.8. Are there questions on this problem? Because you've got several problems in the homework just like it. Yes, sir. Evan. The normal force, if I just look at all the forces in the y direction, I have one force, the normal force, in the positive y direction, and I have one force in the negative y direction. That's this component of the weight. Do you see how I got this one to be 560?
Yeah, sorry, I misspoke. I meant the friction force.
Oh, the friction force. The friction force, because it's kinetic friction, I always just plug and chug into this formula here. Okay, that's the formula that's going to be on the front page of the exam, and you just plug into it. Okay, and the important thing to realize is that in any decent problem, you're going to have more than one normal force. They're just very common. Okay, and so if you're looking for the friction force between the snow and the skier, you better find the normal force between the snow and the skier. These two should have the same indices. And that's another benefit of carefully labeling your forces with those indices. Okay? You see where I get the 56 now? Okay. Other questions on this? Yes.
Isn't that friction force the max force?
Oh, no. In kinetic friction, there's not a maximum friction force. It's just one value. We're going to get to the maximum value, but that's for static friction. Patience, young Jedi. Okay. Okay. Oh, we're here. Ha ha. Static friction. Static friction. Let's talk about static friction, the hard kind of friction, the confusing kind of friction. Suppose I have a ugly block. I looked for a block that had something I could tie onto, and I couldn't find anything in the demo room, so I just grabbed anything that had a handle. Suppose I pull on this with a force of 2 newtons, and it doesn't go anywhere, okay? It just doesn't go anywhere. So if I draw a free body diagram for that block, I've got the weight down, I've got the pull by the spring scale on the block of 2 newtons, and then I have the table pushing up with a normal force and a friction force that I draw is really big because it didn't go anywhere. I'll wait. No one's going to call me a liar? Stick and wrong?
Shows that it's accelerating to the right.
Yeah, this says the block is racing towards that door. That would be spooky. You'd all be running for that door. Yeah, that's not what's happening. By Newton's second law, with zero acceleration, if I'm pulling to your left with 2 newtons and it's not going anywhere, the friction force has to be 2 newtons. But I could also pull with 4 newtons and it doesn't go anywhere. In that case, the friction force would be what? Yeah, 4 newtons. I can pull with 16 newtons, and if it doesn't go anywhere, that means the friction force is 16 newtons. I could have done 13.2 newtons. All sorts of values. It can be anything it needs to be to keep those surfaces from moving relative to each other. Up to a point, up to a maximum value, okay? At some point, I'm going to pull so hard that those nooks and crannies can't keep the surfaces together, that they break apart, okay? Let's say that happens at 16.01. If I pull that hard, it takes off, it moves. Well, what do you know about the friction force then? How big has it got to be now? Yeah, it's got to be smaller than 16, because I know that now it's the diagram screaming to your left. It's taken off. I also know that it's now kinetic friction, and it obeys that simple formula. But before it started moving, when it was static friction, when there was no relative motion, I didn't have a simple formula. I didn't have something I could plug into. But I knew what the value was. I knew when it was 2. I knew when it was 4. I knew when it was 16. How did I know? What was I using? What law was I using? Newton's second law with 0 acceleration, okay? Now, static friction adjusts to the demands. It could be anything it needs to be up to a point, okay? And 99.5% of the time, we use Newton's second law to figure out how big that static friction is. The only time that you don't is when you're right on the verge of breaking free, when you're right on the verge of breaking loose, okay? Now, let's talk about that maximum value of static friction when it breaks the surfaces apart. It turns out that that maximum value also depends on 2 things: how rough the surfaces are and how tightly they are pushed together. You notice that that formula looks very similar to the formula that we have for kinetic friction, except that we've got a different coefficient. For every 2 surfaces, we always have 2 separate coefficients, one for sliding friction and one for static friction. Now, this formula is going to be on the front page of the exam, and it's going to be labeled static friction, and you're going to be tempted to use it. But this is not a formula. I repeat, it is not a formula for static friction. It is a formula for the maximum static friction. How big the friction can be before the surfaces break loose from each other. Okay, quick clicker question. You're going down the road on a dry day. You're not 16. You don't want to peel out. You don't want to be screeching as you go down the road. What kind of friction is desired between your car tires and the road? Do you want kinetic friction, static friction, or both? Go ahead and click. Okay, last call. Okay, it's either static friction or both, but it is definitely not E. Okay, that person needs to lap themselves and then giggle. Okay. There we go. Perhaps this will help. These are wheels, and you can see that you don't want the bottom of that wheel moving relative to the ground. You want those treads to just be stuck in the mud as the wheel rolls over them. Well, the same is true for a regular tire. The part that's in contact with the road is just a smaller surface, but you don't want any movement between that bottom of the wheel and the road. That's what causes the screeching as you're spinning your wheels, okay? And so what we want is just static friction. Just static friction. You want no motion between the bottom of your wheel and the road. Okay? Now, here's a summary. Static friction can be anything in this range from 0 up to this maximum amount. Anywhere in there. But kinetic friction always just obeys this formula right here. And this this kinetic friction is always going to be smaller than that maximum value of static friction. Okay? Always that value. Now, let me see if I can help make this sense. Help make this make sense. If it's winter and you get yourself stuck in a little bit of a ditch with ice, and you want to get out of that situation, you don't want to put your car into first gear and floor it, because then your wheels are going to be spinning and you're going to be stuck with this kind of friction. And that's usually not the kind of friction that's going to get you out of the ditch. Okay? What you want to do is put your car into second gear and just ease on the gas. And as you push those nooks and crannies against each other, you move your static friction up and up and up and up and up and up, but you don't want to push too hard or you'll go past this maximum and then suddenly your wheels are spinning and you're stuck back here again, okay? When I'm teaching in Montana, this is obvious because it's winter 10 months of the year, okay? So here's another way of looking at it. Take your hands and put them together like this. This hand represents the nooks and crannies at the bottom of your wheel. And this hand represents the nooks and crannies on the road. And if there's no motion between those, there's chemical bonds that form. Now, the harder I pull against one, the harder those nooks and crannies are pulling on each other, okay? And I can pull so hard on one of those objects that the nooks and crannies just break free. And suddenly I've broken off my fingers and I've just got bloody knuckles against bloody knuckles. Okay, is that a visual? Okay, and so that's not as big a friction as when I actually have these bonds going on. But once I break the bonds, it's just rough spot against rough spot. That's a smaller friction. See if your neighbor's on the bus. See if your neighbor understands what we're doing here.
So can I have static?
What should that diagram screen? Left, right, or 0? So it has to be screening 0. And you only get one friction point. If it's left, the string's wrong, and if it's right, the diagram string's wrong.
Right.
No friction. We'll talk about that on Thursday, right at the beginning of the class. Okay. If you turn that page over that I gave you, that was given to you, there's an old exam question. An exam question that most of the class got wrong, and that makes it a wonderful teaching question, okay? Now, what you've got there is a, whoops. To start with, if we just look at the first parts, A and B, You just have a block A that is 25 kilograms and is being pulled across a floor at a rate of 2 meters per second every second is the acceleration. We're told that the coefficient of kinetic friction between the floor and the block is 0.3. So really quick, do parts A and B of that exam question. And then we're gonna use our clicker to share our answers. If you get done with A and B, you can go on to part C. Okay, let's talk about parts A and B. The friction force exerted by the floor on the block A is, use your clicker. Tell me what you got for an answer. Remember, this is the easy kind of friction. Okay, last call, get your vote in. Okay, the correct answer is 75. So let's look at that. Again, even though it doesn't ask you to draw a free body diagram there, it's always helpful to do so. The first force I put on there is the weight force. With 25 kilograms, I would have a weight force of 250 Newton. Then ask, are there any magnets? No. What touches the block? I have the rope pulling. I have the floor pushing with a normal force, and I have a friction force. Now, I've already used Newton's second law in the y direction. Because there's no acceleration in the y direction, my diagram has to scream balance in the y direction. I can find my friction force. It's the easy kind of friction. So I just plug into my formula, wrong one, just the mu sub k times the normal force 0.3 times 250 is 75. Okay, and so that's my answer, 75. Everyone see how we got that? Now, in part B, you're asked to find the tension force in the rope. Now, let's go back. This diagram obviously needs to screen to the right because there's acceleration to the right, 2 meters per second squared. So the question is, how big does that tension force have to be in order to get that scream? Now you can click. Okay, last call. Still need a couple votes. Come on. Good. The answer is E, 125. The diagram has to scream to the right. But the question is always, how loud should it scream? Well, that is always answered by Newton's second law. I want 25 kilograms to accelerate at 2 meters per second squared. That means I need a scream of 50 Newton. That doesn't mean my tension is 50 Newtons. That means I need 50 more Newtons in the direction of acceleration than the opposite direction. If I've got 75 Newtons left, I need 50 Newtons more than that to the right. So I've got 125, because 125 to the right minus 75 to the left is a net or total of 50 to the right. That makes sense? Okay, now part C. You were asked to draw free body diagrams. We always draw free body diagrams of the simplest object first. In this case, that's going to be block B. So quickly, just draw a free body diagram for block B. Don't worry about block A right now, just block B. Remember, we're told that the coefficient of static friction between A and B is large enough that they move together. They move together as one. Okay. Well, I hope that everyone got a free body diagram like this. Okay. That I've got the weight of block B down. The only thing touching B is A, and it pushes. And when one thing pushes on another, there will always be a normal force. There may also be a friction force. Well, how did I know that that friction force was to the right? Well, what do I want that diagram to scream? Well, I want it to scream that acceleration to the right. Now, when I put this on an exam, a lot of people said, well, Greg, block B is not moving relative to block A. There's no acceleration of block B relative to block A. We don't do our physics relative to block A. We do it relative to the sidewalk, okay? If I buy the most expensive sports car with really expensive leather seats, and I put my hind end in that leather seat, I hit the gas and I go from 0 to 60 in 2 seconds. It's a really fast car, okay? A friend put me in a Tesla Plaid. The only time I've been in a Tesla, and he hit the gas and I, did my butt accelerate? Oh yeah, it felt good. It went from 0 to 60 in 2 seconds, just like the car did. Okay? If A is speeding up by 2 meters per second and B's going with it, B's sped up by 2 meters per second. So my diagram has to scream to the right. But how big is that force, that friction force? With your neighbor, figure out how big that friction, the static friction is on that. This will be the last clicker question, folks. The last clicker question. How big does that static friction have to be?
You have to turn it on.
Oh, thank you. Now you can click. Sure, you're just gonna let me just wander around here for the rest of the day. Humor the old man.
That's pretty chill. That's not a-
When we're drawing the free diagram for block A. Block B.
I'm sorry?
When we're doing the free body diagram for block A. we have to include block B.
No, that's a force on block B. You would include a normal force by B on A, which is the third law companion to that force by A on B.
Oh, that's fine.
Yeah.
Thank you.
Okay, get your vote in. We're running out of time. Last call. We've got 2 minutes, and these are the more important 2 minutes of the lecture, so stay with me. Last call. Okay, the answer would be 80 if this were a democracy. It is not a democracy. Okay. The answer is 20. 20. Wait, here's why. Those of you that said 80, what were you thinking? I'll tell you what you were thinking. You were thinking mu sub s times the normal force, 0.8 times 100 is 80. But that formula is not a formula for static friction. That is a formula for the maximum static friction, the point at which this thing is going to, B is going to slip off the back of A. Okay? What I use 99.9% of the time is Newton's second law. This diagram has to scream to the right. How loud should it scream? I want 10 kilograms to accelerate by 2 meters per second squared. It has to scream to the right by 20 newtons. I've only got one force to the right. It's got to be 20 newtons. Folks, I got you. I got most of you. Don't let me do that to you on the exam. That's why I did it to you in class, so that you wouldn't be tripped up on the exam. Go have a good evening, folks. May the net force be with you.
Do you want Thursday? Yeah, well, yeah.
Well, that's kind of difficult to now.